this problem which said maximize the profit function z given by 250x plus 75y, where x represented the number of tables and y represented the number of chairs, subject to what all constraints? Constraints were 5x plus y is less than equal to 100. This was my investment constraint. Then x plus y is less than equal to 60. This was my storage constraint. And obviously number of tables and number of chairs cannot be negative. So x and y are non-negative. Obviously this is my objective function, and objective is to maximize profit. So this is my profit function. These are all my constraints, and this is my non-negativity restriction. Now when I went ahead to graphically solve it, because that is how we are going to learn to solve an LPP, when you proceed to actually graphically solve it, you first of all have to consider these 3 or 4 constraints. First, second, third and fourth, and you need to actually convert them into equations and draw these straight lines which they are representing. So when I talk about the equation 5x plus y equals 100, what do you get? When you put x equals 0, y is 100. When you put y equals 0, x is 20. So you actually get a straight line somewhat like this. This point is 0, 100, and this point is 20, 0. This is my straight line, that is 5x plus y is equal to 100. Fine. After that, we see that this line is dividing this entire coordinate plane into 2 half planes. Which half plane would be the region represented by the inequation 5x plus y less than equal to 100? For that, you pick up any point on one of the half planes. Here in this half plane lies origin, so I see whether origin is satisfying this inequation or not. You put x equals 0, y equals 0, 0 plus 0 is definitely less than 100. So points on the line and points lying on this side of the line is the region represented by this inequation. Moving to the next, x plus y less than equal to 60. Consider the equation x plus y equal to 60. When x is 0, y is 60. When y is 0, x is 60. So you basically get something like this line. This is 60, 0, and this point is 0, 60. Fine, this is the line x plus y equal to 60. Again, what is the region represented by the inequation x plus y less than equal to 60? You can see that x plus y equal to 60 is a line which is dividing this entire coordinate plane into 2 half planes. Which half plane is going to be representing the region represented by this inequation? For that, pick up any point lying on any one of the half planes. Suppose I pick up origin. Put x equals 0, y equals 0, 0 plus 0 is 0, which is definitely less than 60. So this region, that means points on the line and points lying on that region where origin lies, this side, is the region represented by this inequation. After that, you had x equals 0, y equals 0. X equals 0 is y axis, y equals 0 is x axis. This is my y axis, that is x equals 0, and this is x axis, that is y equals 0. I want x greater than equal to 0, y greater than equal to 0. X equals 0 is this, greater than 0 would be this side. Right, this side you pick up any point, x coordinate is positive, and over here on the y axis you pick up any point, x coordinate is 0. So x coordinate is 0 or positive when points are on the y axis and on the right of the y axis, that means in the first and the fourth quadrant. So the region represented by x greater than equal to 0 is complete first and fourth quadrant along with the y axis. Region represented by y greater than equal to 0, y equals 0 is all the points lying on the x axis, because any point you pick up on the x axis has y coordinate equal to 0. What are the points which have y coordinate greater than 0? All the points lying in the first and the second quadrant. So region represented by y greater than equal to 0 is nothing but first and the second quadrant and the x axis. When you talk about those points which are satisfying this inequation also, this inequation also, this inequation also, this inequation also, you actually are interested in finding that region which is the intersection of all the regions represented by all the 4 inequations. And when you actually consider that region, it comes out to be this region. Yes, this is that bounded region which happens to be the intersection of all the 4 regions represented by the 4 inequations given in the LPP. So you can see all the boundaries are there and these 4 corner points are there. This is my boundary, 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 inside region, and these 4 points I will be marking as A, B, C and D. Is it clear? I already told you that these, the points lying in this shaded region along with these boundaries are the points which are satisfying all the 4 constraints and therefore are said to be feasible solutions, right? They are representing x comma y ordered pairs which are satisfying investment constraint, storage constraint and non-negativity constraints. That means the dealer can definitely move ahead with buying x number of tables and y number of chairs where x comma y is belonging to this feasible region. Clear? Because in that case it will be not violating his investment constraint, not violating his storage constraint and not violating his non-negativity constraints. So he can definitely pick up any of these infinitely many options of buying tables and chairs. But actually, if this is the set of all feasible solutions, I say this is my feasible region. Fine. This region that you can see, bounded region completely shaded along with the boundaries, is known as my feasible region. He is not wishing to find those number of tables and chairs which actually are going to satisfy all constraints, but along with satisfying constraints it should also be able to maximize my profit function. What is the strategy to pick up that feasible solution out of infinitely many feasible solutions which also along with satisfying constraints maximize my profit function is something I would be decoding to you just in a short while. Okay, so the entire venture is to find that one ordered pair x comma y which is not only going to satisfy my constraints but also is going to give me the maximum value of z. All the points which are satisfying all my constraints are lying in this feasible region. So which point or points from this feasible region I will be picking up which will be maximizing z, that requires a strategy. In order to get to that strategy, there are certain points we need to note which are utterly important. What are they? Let's write down. First thing, always remember that the set of all feasible solutions, the set of all feasible solutions of an LPP is a convex region. Feasible solutions means those ordered pairs x comma y which are going to satisfy all my constraints. Like this is the set of all feasible solutions and right now it is a convex region. What do I mean by convex region? Right now if I draw this figure, all this region I consider, I am saying this is a convex region. Convex region means you pick up any 2 points in this region. In this region you pick up any 2 points. If you will be joining them, the line segment joining them will be completely lying in this region. The line segment joining them will be completely lying in this region. Pick up any 2 points. Pick up this point, pick up this point. Any 2 points in the region if you pick up, and when you talk about the line segment joining them and it completely lies in the region, then you say this is a convex region. Whereas if I talk about this, say this region, then this is not convex because yes, there are 2 points which I am picking up in this region, but when I join them, the line segment completely does not lie in the region. So when you pick up any 2 points in the region and the line segment joining them lies completely in that region, you say that region is a convex region. And if there are even one set of points, one pair of points which are lying in the region but the line segment joining them is not completely lying in the region, you say that that region is not a convex region. So in here, the thing that you need to always keep in mind is that the region which would be represented that as the feasible region of the LPP will always be a convex region. Right now also you can see this is a convex region. You pick up any 2 points in this region, join them, the line segment will also be completely lying in the region. So the set of all feasible solutions is what is known as my feasible region of the LPP. And the first point is that the feasible region of an LPP is a convex region. Now what happens is an LPP need not always have an optimal solution. Yes. It's not always true that a linear programming problem will definitely have an optimal feasible solution. That means an ordered pair x comma y which not just satisfies all the constraints but also maximizes my profit. It may not always exist. Okay? There are LPPs which don't have any optimal feasible solution. But now the third point holds utterly important. There is this fundamental extreme point theorem. Fundamental extreme point theorem there is, which says what? Yes, an LPP need not always possess an optimal feasible solution, but if an LPP possesses an optimal feasible solution, suppose it possesses an optimal feasible solution, then it occurs at one of the corner points, or you can also say vertices of the feasible region. Yes, this is utterly important. Right now we were struggling that out of so many, infinitely many feasible solutions, which is that feasible solution which is my optimal feasible solution? And the answer is given to us by the third point, that if an LPP will be possessing an optimal feasible solution, it will either be point A or point B or point C or point D. That means only one of the corner points can actually give you the ordered pair x comma y, which is obviously going to be feasible solution because it is satisfying all the constraints. You can see all these 4 points A, B, C, D are corner points of my feasible region only. That means they are feasible solutions because the boundaries are included in this feasible region. So these corner points are definitely feasible solutions, but it is one point among these 4 points only which will be giving me the maximum value of z. Any point you pick up from apart from these 4 points will never be able to give you the maximum value of z. Okay? If this LPP possesses an x comma y which gives you maximum value of z along with satisfying the constraints, then it has to be one of these corner points only. And so our discussion and query has been reduced to just 4 points. Now I am not going to be confused as to which point among these infinitely many points is going to maximize my value of z. In fact, I have only 4 points A, B, C, D. I will be picking up all these 4 points. Of course, they are already satisfying my constraints. I will be picking up these 4 points and plugging in the value of x and y in here and seeing which ordered pair is giving me the maximum value of z. Okay, so my entire discussion is going to be boiling down to just the corner points. Find out the feasible region and then pick up the corner points. At one of the corner points only, the maximum value of z will be obtained. So check the value of z at all the corner points. Whichever corner point gives you the maximum value of z, that is my optimal feasible solution. Of course, these corner points are already feasible solutions. They are lying on the boundary of the feasible region, right? And the boundary is involved in the feasible region. So they are of course my feasible solution, but they will be optimal when they are able to maximize my z. So this fundamental extreme point theorem is extremely important. This is what lays down the entire foundation of getting an optimal feasible solution for an LPP, that if an LPP possesses an optimal feasible solution, it may happen that it may not possess any. If it is possessing, then it will definitely be existing or occurring at one of the corner points of the LPP only. Now many a times it happens what? That at point C which is 20, 0 for example, at point C I am getting a particular value of z, and at point D I am getting the same value of z. The coordinates of D are different, but I am getting the same value of Z, for example. And at A and B, I am getting value of Z which is lesser than that. That means point C and point D. At point C and point D, I am getting maximum value of Z out of all the 4 corner points when I am plugging it in the definition of Z. Point C and point D are 2 different coordinates which are giving me the same maximum value of Z among the value of Z obtained for these 4 points. That means 2 feasible solutions are optimal feasible solutions. It may happen like that as well. It may happen that none of the points are able to give me maximum value of Z. In that case, LPP will not possess an optimal feasible solution. It may happen that more than one point, suppose B and C are 2 distinct points at which I am getting the same maximum value of Z. In that case, I am getting 2 optimal feasible solutions, right? But whenever you get 2 optimal feasible solutions, suppose B and C are my 2 optimal feasible solutions which are 2 distinct points but are giving me the same maximum value of Z out of the value of Z obtained at all the 4 corner points, then these 2 qualify to be optimal feasible solution. But in that case, only these 2 are not optimal feasible solution, but in fact the line segment joining them, if you consider, it says the solution set of this inequation is what? Let's talk about the solution set of this inequation, which is 2x plus y greater than 5. So first of all, what you do, you consider this to be an equation, right? You consider this to be an equation, and this, if you consider to be an equation instead of inequation, you get a straight line in your 2D plane. So what do you get? 2x plus y is equal to 5. This is what you consider. Draw this straight line. When you put x equals 0, y turns out to be 5. So suppose this point is 0, 5. When you put y equals 0, x turns out to be 5 by 2, which is 2 point something. So here is suppose that. Fine. So when you have 5 by 2, you get 2.5. So in here basically, if this is 2.5, you have this point and this point. When you join and extend is what you get, the straight line 2x plus y equal to 5. I am interested in the region represented by 2x plus y strictly greater than 5. I am not interested in the set of points for which 2x plus y is equal to 5. So all these points lying on this straight line are actually satisfying 2x plus y equal to 5. I am not interested in such points. So I draw this line as a dotted line. I draw this line as a dotted line because I am not wanting to collect all those points which are satisfying 2x plus y equal to 5. I am interested in the set of points which satisfy 2x plus y is greater than 5. So what do? Pick up any point which is not lying on this line, origin. Put x equals 0, y equals 0, you get 0 plus 0. 0 plus 0. 2 into 0 is 0 plus 0. 0 plus 0 is greater than 5. This is false, and therefore the region not containing the origin is going to be the region represented by 2x plus y greater than 5. This side will not be my region. Points on the line will not be in the set. Only the points on this side of the line is going to be the set of all those points x comma y which are satisfying 2x plus y strictly greater than 5. So this is the region represented by 2x plus y greater than 5. Okay, this is the region represented by 2x plus y greater than 5, and so the region is half plane that contains the origin, no. Open half plane not containing the origin, yes. This is my answer. This is an open half plane which is not containing my origin. Moving to the next question, we have objective function of an LPP is what? So you all know objective function of an LPP is not a constraint. It is actually a function to be optimized, either maximized or minimized. It is a function to be optimized, linear function to be optimized. It is, yes, a relation of the variable, but a more apt option is that it is a function to be optimized. Moving to the next, we have, which of the following is not a convex set? Now see, in here you should always know what these regions are going to turn out to be. Then it becomes very, very easy for you to conclude about them representing a convex set. First is 2x plus 5y strictly less than 7. We just now dealt with such a case. 2x plus 5y strictly less than 7. Consider 2x plus 5y equal to 7. When you put x equals 0, you get y equals 7 by 5, which is 1 point something, and when you put y equals 0, you get x equals 7 by 2, which is 3 point something. Fine. So somewhere here is 3, somewhere here is 1, this is 1 point something, 3 point something, and so when you join these two, you actually get the straight line representing 2x plus 5y equal to 7. Because I am not interested in the points which satisfy 2x plus 5y equal to 7, this line will be drawn as a dotted line. Is it clear? This line will be drawn as a dotted line. Now I want all those x comma y for which 2x plus 5y is strictly less than 7. Take up any point which is not lying on this particular line, suppose origin, put x equals 0, y equals 0, 0 plus 0 is less than 7, this is true, and therefore the region represented by this is this. The region represented by the inequality 2x plus 5y strictly less than 7 is this region. This is that region represented by this inequality. Is this a convex set? Yes, of course it's a convex set, because you pick up any 2 points in this region. Anywhere you pick up any 2 points in this region, the line segment joining them is always going to lie in the same region. So this is definitely a convex set. I have to find out which one is not a convex set. This is a convex set. What about this, x square plus y square less than equal to 4? If I talk about x square plus y square less than equal to 4, this is nothing but a circle with center at origin and radius equal to 2. If I talk about x square plus y square equal to 4, it is a circle with radius 2 centered at origin. And x square plus y square less than equal to 4. Equal to 4 is all the points on the boundary of the circle. X square plus y square equal to 4 is actually being satisfied by all the points on the circle. I want all those points x comma y which satisfy x square plus y square is less than 4. For that I will have to pick up a point which is not lying on the boundary, that is origin. So if I plug in x equals 0, y equals 0, I get 0 plus 0 is less than 4, which is true, and therefore the region consisting of the origin is going to be my feasible region. So the region represented by x square plus y square less than equal to 4 is the points inside the circle and the points on the boundary. Is this a convex set? Yes, of course. You pick up any 2 points in this region, the straight line joining them is always going to lie in the same region. So even this is a convex set. I am going to say this is a wrong option because I want to find out which is not a convex set. What is this? All those x such that mod x is equal to 5. All those x such that mod x is equal to 5. Mod x equals 5 means what? I can rewrite this as mod of x minus 0 equals 5. That means distance between x and 0 is 5. Which are the points on the real line whose distance from 0 is equal to 5? Obviously 5's distance from 0 is equal to 5 and minus 5's distance from 0 is equal to 5, right? These are the only 2 points whose distance from 0 is equal to 5. So inside this set only 2 points will lie, 5 and minus 5. All those x such that mod x is equal to 5 is the set consisting of 2 points minus 5 and 5. Can this ever be a convex set? No. The set consisting of discrete points, finitely many discrete individual points, can never be a convex set, because if only these 2 points are there in this region, then the straight line joining them is never ever going to lie in this set, because the straight line joining them is going to consist of infinitely many in between points which are not there in my set. So it is this particular set which is not a convex set. And this is clearly representing an ellipse. You can write this as 3x square upon 6 plus 2y square upon 6 equal to 1. That would give you x square upon 6 upon 3, that is x square upon 2, that is x square upon root 2 square. 2y square upon 6, which is y square upon 3, that is y square upon root 3 square. So it will be x square upon root 2 square plus y square upon root 3 square equal to 1, and that is going to give you an ellipse with major axis along y axis, x square upon root 2 square plus y square upon root 3 square equal to 1. I want less than equal to 1. If I bring 6 over here, this is 3x square upon 6 plus 2y square upon 6 less than equal to 1. Equal to 1 is satisfied by all the points on the boundary. Less than 1 is obviously satisfied by all the points inside the ellipse. Because when you put x equals 0 and y equals 0, you get 0 plus 0 is less than 1, which is true. So this happens to be my region represented by 3x square plus 2y square less than equal to 6. And this is clearly convex because you pick up any 2 points in this shaded region. Boundary is also included. When you join those 2 points, the straight line consisting of those 2 points, joining those 2 points is lying in the same region. So even this is a convex set, so this is a wrong option. Fine. Moving to the next, we have which of the following statements is correct? Every LPP admits a solution, wrong. An LPP admits unique optimal solution, wrong. We have witnessed LPPs which have more than one optimal solution. A is wrong, B is wrong. If an LPP consists of 2 optimal solutions, then it has infinitely many optimal solutions. This is true. If you have 2 optimal solutions, then all the points on the line segment joining those 2 optimal solutions are also optimal solutions. So whenever an LPP admits 2 optimal solutions, all the points on the line segment joining them are also optimal solutions. So there are infinite number of optimal solutions. Clear? And then it is written the set of all feasible solutions is not a convex set, which is false. We have done this as a theorem that the set of all feasible solutions of an LPP is definitely a convex set. In fact, it's a convex polygon. By graphical method, the solution of this linear programming problem would be what? Let's begin. We need to plot all the constraints and also take into consideration this non-negativity restriction. Let's begin the plotting. You all know how to carry out the process. 3x1 plus 2x2 equal to 18 you will be considering. First constraint, when x1 is 0, x2 is 18 upon 2, that is 9. When x1 is 0, x2 is 9. When x1 is 0, x2 is 9. When x2 is 0, x1 is 18 upon 3, that is 6. So this is 6 comma 0. Fine. If you join them, this gives you the equation of the straight line 3x1 plus 2x2 equal to 18. You are interested in 3x1 plus 2x2 less than and equal to. So all these points will definitely come. I need to decode which are the points which satisfy 3x1 plus 2x2 less than 18. For that, put x1 equals 0, x2 equals 0 because 0 comma 0 is not lying on this line. This gives you 0 plus 0 is less than 18, which is true. So everything on this side of this line is going to be my region represented by 3x1 plus 2x2 is less than equal to 18. Then you have x1 less than equal to 4. That means x1 equal to 4 is going to be this line. This is x1 equal to 4. So this point will be 4 comma 0. I want x1 less than equal to 4. So everything on this side. And then you have x2 less than equal to 6. So 6 is going to be somewhere here. This is x2 equal to 6. Less than equal to 6 would be below this line. And x1 greater than equal to 0, x2 greater than equal to 0 is going to make you fall in the first quadrant. So in the first quadrant, on this side of 3x1 plus 2x2 equal to 18, below x2 equal to 6, to the left of x1 equal to 4, the common region comes out to be nothing but this. What are these points? This point is 0 comma 6. I can say this is my feasible region. Firstly, this is my feasible region which is bounded, and therefore I just need to pull out all the corner points, find out the value of z over there and see what is my optimal solution. So let's do that. What is this? This is the intersection of 3x1 plus 2x2 equals 18 and x2 equals 6. If you put x2 equals 6, you get 6 into 2, 12. 18 minus 12 is 6. 6 upon 3 is 2. So x1 is 2, comma 6. And here, what is it that you get? This is the intersection of x1 equals 4 and this line, when you put x1 equals 4, you get 4 into 3, 12, 18 minus 12 is 6, x2 would be 6 upon 2, that is 3. So this point would be 4, 3. x1 is 4, x2 in that case is coming out to be 3. So my corner points are 0, 6, 2, 6, 4, 3 and 4, 0 of the feasible region. Z is 3x1 plus 5x2. Three into 0 is 0, 5 into 6 is 30, 3 into 2 is 6, 5 into 6 is 30, so this is 36, 4 into 3 is 12, plus 5 into 3 is 15, this is 27, 4 into 3 is 12. You are interested in maximizing, right? Maximum value is 36 being obtained at 2, 6. So the solution is 36 which is being obtained at x1 equals 2 and x2 equals 6. Clear? Next I have the region represented by this inequality or this inequation system is what? Let's see. X and y are given to be non-negative, that means the portion which is being represented by this inequations is the first quadrant. Then I have x plus y greater than equal to 2, x plus y greater than equal to 2. I have drawn this line of x plus y equal to 2. So this point would be obviously 2, 0 and this would be 0, 2. When you put x equals 0, you get y equals 2, y equals 0, you get x equals 2. This is x plus y equal to 2. I want greater than equal to 2. Greater than equal to 2 would be what? If you put x equals 0, y equals 0, you get 0 plus 0 greater than 2, which is false. So the region containing the origin is not going to be the shaded region. This would be the shaded region which is not containing the origin. Fine. Then you have x plus 2y is greater than equal to 3. X plus 2y is equal to 3 is first of all you consider. When you put x equals 0, you get y as 1.5. So somewhere here. And when you put y equals 0, you get x equals 3. When you join them, this is what you have as x plus 2y equal to 3. You want not just equal to 3 but greater than equal to 3. When you put x equals 0, y equals 0, you get 0 plus 0 greater than 3, which is false. So everything on this side of the line which is not containing the origin is my shaded region, and therefore when I talk about the intersection of region represented by this inequation and the first quadrant given by x and y non-negative, I actually get what region? The intersection comes out to be this region. This is what the intersection comes out to be.